want to welcome you to my lecture today. Of course, today we're going to finish our review of the midterm 2, since uh, of course, next week we're going to have midterm 2. Before I get started today, uh, I realize I've not been seeing any one of you in my office hour. I think I want to say this. My office hour is on the Canvas and it's Zoom. Okay, so please, in case you need maybe clarification or you want to meet with me, please meet with me in my office hour, not in person. It's through the Zoom. You can be anywhere in the world, to attend my office hour. Does that make sense to everyone? Okay. Now, uh, what I want to do today, I want to focus more on distributions. I'm going to review, I'm going to summarize probability distributions, the discrete type and the continuous type. That is going to be the focus today. Okay, so I'm going to tell you, because in the exam that is coming on, how will you identify a particular distribution? So that's why what I want to do today, I will actually review with you the discrete type distribution and the continuous type distribution. And what I want to do is going to be on the board. Now, I'm going to, we have two types. As far as probability, okay, distribution, okay, is concerned, we got two types. Number one, we got discrete type, okay, and we got continuous type. Okay, now we got discrete type, we got continuous type. Before we can actually understand a particular random variable, we need to know how that variable is distributed. If it's a discrete random variable, it's going to follow one of the discrete type probability distribution. If it is continuous random variable, it's going to follow a continuous type, one of the continuous type probability distribution. Now, let me tell you that under the discrete type, okay, I remember we started working with Bernoulli. We talk about binomial. We talk about Poisson distribution. We talk about multinomial. Okay, we talk about hypergeometric. Okay, we talk about geometric. Okay, and we also talk about negative binomial. Okay, now I remember we talk about all these distributions under the discrete type. Okay, so what I want to do now, I want to revisit them and tell you what they do. We started with the Bernoulli, and I said a random variable x follow Bernoulli with a parameter p. Of course, we use Bernoulli distribution where we have two possible outcomes, and the numbers of trial is 1. The probability mass function for Bernoulli, okay, is actually p raised to power x, 1 minus p raised to power 1 minus x. And of course, the random variable is x0, s equal to 0, 1. In a Bernoulli distribution, okay, in a Bernoulli distribution, the x represent the numbers of sources, and n, okay, the numbers of trial n equal to 1. If I try once, it's either I see a 0 sources, or I actually see 1 sources. Now, so when you take a look at the Bernoulli distribution, expected value of x, we found that. The variance of x, we also find out. Okay. Okay, q is 1 minus p. Okay. Now, this is Bernoulli distribution. Any question on Bernoulli distribution? Okay. You can be asked to derive the mean and variance for that. And don't forget, when we want to derive mean and variance for any discrete type probability distribution, if you want to derive the mean, of course, you know the expected value of x is going to be summation x, f of x. In this case now, the f of x, your f of x is the same thing as your probability. That, and your, for Bernoulli is s is going to start from 0 to 1. You take a look at the state space. Now, from there, I want to move to binomial. Binomial is an extension of Bernoulli with a binomial. We're still talking about two possible outcomes, except that the numbers of trial is more than 1. When s follow, so under binomial now, okay, when s follow binomial distribution with parameter n and p, the probability of x equal to that will be n combination s p raised to power x 1 minus p raised to power n minus x. Here the state space is basically going to go to n. This is binomial distribution. Binomial perform the same job with Bernoulli, except that the numbers of trials in binomial is more than 1. The numbers of trials in Bernoulli is 1. And of course, the event here is, is characterized, by two possible outcomes. Of course, we can find the mean in binomial. It's going to be NP. The variance of x in binomial is going to be NPQ, or you say NP into 1 minus P. Don't forget, using the idea of P plus Q equal to 1. Take a look at that. So using the idea of, so this is binomial distribution, the probability mass function, and the mean and the variance. In every go ahead. No, you do a square root for the standard deviation. For instance, if I say standard deviation now, just going to find the square. You're just going to put the square root. That's a good question. Okay. In binomial distribution, n is the number of trials, x is the number of sources that I got. P is the probability of success, and that is why it's carrying the number of sources. The probability of success is going to carry the number of sources. 1 minus P is the probability of failure, that we also call Q. Okay? is basically going to carry the numbers of failures. Because if N is the numbers of trials and S is the numbers of success, the numbers of failure is going to be N minus X. And that's why the probability of failure is carrying down. When I try 10 times, how many times do I record the number of characteristics of interest? Okay, from here, I'm actually going to move from binomial now. I'm going to move to hypergeometrical distribution. Now, when I talk about hypergeometrical distribution, hypergeometric distribution and binomial, they're doing the same thing, except that what distinguishes them from each other is the fact that is a mode of sampling. In binomial, we're sampling with replacement. In hypergeometry, we sample without replacement. Okay, so the probability mass function, okay, for hypergeometric is basically going to be N minus K, and I'm basically going to have this N minus X divided by N combination N, and here S start from 0, 1, 2 up to N. Okay, where maybe this is where K, maybe this is defective and this is not defective. Okay, in terms of politics, if you're talking about only Democrats and Republican in the United States, it's either one belong to Republican Party or one belong to the Democrats. If I want to choose, okay, politicians, if I want to choose Democrat, then I'm actually going to choose from the population of Democrats. If I want to choose Republican, then it has to come from the population of Republican. Okay, so, and here the sampling is done without replacement. Even though we're also talking about two possible outcomes. And of course, the mean here, okay, it is this guy here, where this guy, the number of the characteristics of interest in the population divided by the totality is the same thing as P. The variance here is basically going to be this guy, 1 minus this guy, probably N minus K divided by N minus 1. Okay, when you take a look at this guy, it's more or less like NPQ. This is like a P, this is like a Q. This is the correlation factor, the variance of hypergeometric distribution and that of the binomial. They are not the same. The difference between them is this guy, but the mean is the same. Okay, go ahead. Do you see N minus what? Yeah, I said N minus K over N minus 1. So what do you say? Oh, you mean this guy? Oh, let me see. Let me do my research now. Yeah, the correction factor should be independent of K. You should be right. I'm going to check that. I think you are kind of right, because the correction factor should be independent of K in a way. You can check your notes. Okay. You know, we've already done all of that. Okay. So yeah, I think it should be. Yeah, go ahead. You need to know how to derive it. when you talk about discrete. The only one that I told you that you don't need to worry about is T distribution and F distribution, because the proof is going to take so long. You know, this course is also going to be theoretical. That's why it's different from the conventional 3021. Does that make sense? You need to know how to know, you need to know how, I think I did all this in class. You can check the lecture note. Does that make sense? I think this is the way this should be. Yeah, it should be, the correction factor should be independent of K. Okay, now, from there, I want to move to multinomial. Okay, the multinomial is, the multinomial is when the multinomial, you know, when the numbers of categories is more than 2. Okay, and we are still sampling with replacements. Okay, for instance, if I want to write, it's basically going to be this x1 comma x2, maybe until I get to sk. We're partitioning this guy into K group, not just 2 groups anymore in binomial. And each of these is going to have their probability. So maybe P1 carry X1, P2 carry S2, until I get to PK carry SK. Any question? Any question on this? Any question on the way this is done? Okay. Now, this is multinomial. This is multinomial. Now, the next one that we talk about is Poisson distribution. I told you the multinomial is when the number of possible outcomes is more than 2. Okay, got more than 2 groups. Now, Poisson distribution now, we use Poisson distribution to model rare events. Event that occur in a blue moon. I told you the other time. Okay, the numbers of snake bites in a year, the number of bankruptcy, the numbers of bank failure, the numbers of earthquake, the numbers of accidents within a particular interval. Okay, rare events in general. You know, X follow Poisson distribution with parameter lambda. A probability of X equal exponential raised to power lambda, negative lambda, lambda raised to power X over X factorial, S start from 0, 1, 2 to infinity. You need to know lambda. The lambda is called rate parameter before you can figure out, before you can use this distribution. They say Poisson distribution. Okay, when they give you lambda in day, and they ask question about 2 days, you're going to multiply your lambda by 2. You know, just take a look at what we have in the lecture notes. We use this guy, okay? You know, we use this guy when we are actually modeling a rare event. Now, another distribution that we talk about is geometric. You know, when I'm interested in the numbers of failures I'm actually going to have before I record the first sources. I'm going to say that again. How many failures am I going to have before I record the first sources? So maybe I'm trying to say, maybe there's a kind of program going on. Maybe it's a live program on radio, and they ask people to be, the host asks people to be calling in. Of course, you know, a lot of people will be calling in. How many times am I going to make a phone call before my you know, my call will be connected? Okay, so that's going to be geometric distribution. So X follows geo with a parameter P, because in a geometric distribution, we still have Bernoulli process. Okay, because when you make the first call, it's either it connects or not. That's Bernoulli. Every attempt is either it results in connection or not. You know that, right? Okay, so if I want to write a probability mass function for this guy now, I'm actually going to have this and x minus 1, where s is going to start from 1, 2 up to infinity. You know, the other time you can be asked to, the mean here is lambda, the variance is lambda, the standard deviation will be square root of lambda. So take note of that for Poisson. We can ask you to derive that. Okay. Now for geometric now, okay, the expected value of x is 1 over p. The variance of x is p over q squared or something. Let me see. Is it p over q? I'm going to check. 1 over p or q over p squared. Q over p squared. I think it should be this guy. Q over p squared in a way. So you can check your notes. So this is geometric. You can see that in each of the distribution, I've been writing the mean and variance, right? Okay. So this is geometric distribution. Now we can also have a general version of geometric. The general version of geometric is negative binomial. Negative binomial. The negative binomial, I'm actually going to have this guy. Now, when you take a look at this guy and this guy, this is a general version of this guy. If you plug in r equal to 1 here, you're gonna find yourself here. So this guy is gonna say, okay, how many times am I actually gonna fail before I started recording a good number of successes? Not just success, it's not going to be the first success. Maybe they mention second success, third success. Okay, this is a generalization of that. You know, x in each case does not represent the number of successes as we have in binomial. The number, you know, x here represents the numbers of failures before you record success. Okay, but your p still remain the probability of success. So if the expected value of x here is just going to be the generalization of that, the variance of x is just going to be r. You see that, right? If I plug in r equal to 1 here, I'm actually going to get the mean and variance of the geometric. Any question? Any question? You know, I told you what we use this for in real life. Okay. Now, this is used like if I want to figure out how many times am I going to fail before we record first success. We use geometric for that. How many times am I going to fail before we record a good number of, not just first. This one is going to say we're not experiencing first success for the first time. Here we are in geometric, we're experiencing success for the first time after failures. But here, okay, it's not first time. Does that make sense now? Okay. Now these are discrete distribution that we did. Now, I want to go into continuous now. Like I said, I'm not going to tell you in exam whether a question requires you to use binomial, Bernoulli, geometric. You are going to be the one that will figure it out. But you know, only way I'm going to tell you in continuous. You know, when I ask a question on that continuous, I will tell you the type of probability distribution that I'm talking about. Does that make sense? Okay, now I want to review that of continuous now that we've done in this course. Now, in this course, you know, when you talk about continuous probability, when you talk about continuous probability or distribution, we're actually talking about the distribution in an interval, where the random variable takes value in an interval. I remember I walk you through uniform. I walk you through exponential. I walk you through normal. I walk you through gamma. We did chi-squared. We did beta. We did T, and we did F. How many continuous distribution? Like looking like 8, right? We did all this. You should be able to know how to get the mean and variance of up to beta. Okay. I may not ask you about the derivation of T and F. Okay. Now let's start with the uniform. In the uniform distribution, uniform, you know, X follow unif with parameter A and B if f of x is equal to 1 over b minus a, where s lie between a and b. This is uniform. I remember I walk you through the mean, a plus b over 2. I think the variance was b minus a all squared divided by 12. Okay, so take a look at that. Okay, when the probability of occurrence of an event in the interval is equally likely, we use uniform. I think I gave an example of a gas station the other time where they sell liters of gas or gallon of gas. The probability they're going to sell, if we know the minimum of gallon they sold and the maximum of gallon they sold, the probability of selling a particular number of gallon in the interval is the same. That's what we mean. Uniform. Okay. After uniform, I walk you through normal distribution. From uniform, I go into normal distribution. The normal distribution is the most important distribution in statistics and in research generally because of its simplicity. Okay, there are two parameters in the normal distribution. X follows normal distribution with parameter mu and this guy. If f of x can be written as 1 over square root of 2 pi sigma squared exponential, we have this guy divided by that squared, x lie between negative infinity and infinity. The expected value of x here is mu. The variance of x is sigma squared. Therefore, the standard deviation will be sigma. for your normal distribution. And I also tell you that if you want to apply normal distribution, you actually going to use the standardized aspect, where Z follow normal with mean-zero and variance 1. The f of z will be 1 over square root of 2 pi exponential raised to the power of this guy. Z lie between negative infinity and infinity. The difference between them, if I draw this guy now, if the center here is mu, for this guy, the center is going to be 0. Take note of that. And the movement along the axis here is by amount of standard deviation. The movement along the axis here, the standard deviation is assumed to be 1. If you want to find probability associated with a normal random variable, then we need to get a z-score. Of course, remember that we did z-score. You need to use a z-score x minus mu over sigma. So if they ask you to find the probability of x less than a, okay, it's going to be the same as the probability of z less than whatever values of z you got, depending on the sign. Okay, that's what you're going to have where you normally check table, right? And I said in the exam, I'm going to provide table for whatever distribution I want to test. Does that make sense? That will come with the exam. Now, because of my time, so revise all what we've done in normal distribution. Okay. Now, the next distribution that I talked about was exponential. Exponential distribution. Exponential distribution. X follow exponential with parameter beta. So the f of s equal 1 over beta exponential raised to power this, s greater than 0, beta greater than 0. The exponential distribution is a very good distribution for waiting time before the occurrence of an event. How long am I going to wait before this is no longer going to be working? We don't want a sudden failure, right? And that's why we need to have the life expectancy. The life expectancy of electrical components, okay, can follow exponential distribution. Okay, now here you're also going to have the mean. You're also going to have the variance. Okay, maybe beta and or beta square, you can check. Okay, so we have the mean, we have the variance for the exponential. Like I said, it's used to model the waiting time before the occurrence of an event. Now we also have gamma distribution. When I'm focusing on one component, okay, I'm going to use this guy. But if I now focusing on more than one, then we have what we call gamma, the gamma distribution. So S follow gamma with parameter alpha beta. The f of s equal x raised to power this exponential raised to power this divided by gamma alpha beta raised to power alpha, this greater than 0 and this guy greater than 0. What you see here, what we introduce is the alpha. If alpha equal to 1, we go from gamma to exponential. What is different between the two? The two of them actually model the waiting time before the occurrence of an event, except that with exponential, we actually going to be using, we're focusing on one component, but with gamma, we're focusing on more than one component. The alpha is going to be the number of that component. If alpha equal to 1, you are back at exponential. If you plug in alpha to be 1 here, if alpha equal to 1, this guy is going to be 1, it's going to go away. This is going to go away. The other is going to go away. Okay, this is going to be beta. So it's going to be 1 over, so you are back here. If you plug in alpha to be 1, any question with gamma? And of course, in gamma, expected value of S is going to be alpha beta. And the variance of S is going to be alpha beta squared. What am I saying now? When you plug in 1 for alpha, you're going to give it the property for that of the exponential. That's why I say generalization. Oh, you're struggling looking. Okay, I'm going to make sure. I'm going to make sure okay. This guy here is expected value of S equal alpha beta. The variance of S equal alpha beta squared. Can you see now? Okay, sorry for stressing you, you know. Okay, now exponential gamma. Now I want to go into another distribution that we call chi-square. The chi-square distribution can be derived from gamma here. Okay, the origin of the chi-square distribution can actually be derived from gamma. Okay, now I want to write chi-square. In statistical analysis, we normally, if I want to test relationship between two categorical variables, maybe I want to test how does the level of education affect the level of income, right? We're going to use a chi-square test. But without chi-square distribution, there's no way we can conduct a chi-square test. Now, the chi-square is, how is a chi-square distribution derived? Okay, if alpha equal, okay, so if alpha equal V over 2 and beta equal to 2 in gamma, so I'm actually going to have a new distribution now, f of x now, which is going to be x raised to power V over 2 minus 1 exponential this and divided by, gamma alpha, or 2 raised to power that. So this guy is chi-square distribution. The degree of freedom is going to be V. Okay, so it's like you are having this with V degree of freedom. Okay, so the origin of chi-square was actually traced to gamma. Okay, and not only that, when I square Z, a standard normal distribution, that will give me a chi-square too. Okay, now I want to go into now I told you what we use this distribution for. We want to conduct a chi-square test where you want to test if there's a relationship between two categorical variables. Of course, we need a chi-square distribution to take a decision. Okay, so this is what they use to simulate values in the chi-square table, because I know when they compute the chi-square test value, they need a critical value. Okay, now the next distribution now is beta. Let me tell you this, the beta distribution actually, okay, let me, beta distribution. Okay, do you know that if x follow gamma, okay, with parameter alpha 1, parameter alpha 1, at times I can decide to use one parameter for gamma. Parameter alpha 1 and y follow gamma with parameter alpha 2. Now z equal x over x plus y using the Jacobian transformation. My f of z will be 0 raised to power alpha 1 minus 1, 1 minus 0 raised to power alpha 2. Okay, let me write it. I'm going to write it here so that you can see. Now, f of z will be z raised to power that 1 minus z raised to power alpha 2 minus 1 divided by b of alpha 1 comma alpha 2 that you can also rewrite as this 1 minus z raised to power that gamma alpha 1 plus alpha 2 divided by gamma alpha 1 gamma alpha 2. Now, do you know that this distribution beta was derived where z equal to this? You know, if you want to derive that, we can use another, we can create an artificial variable. The artificial variable will be s plus y. You know, I told you the other time, right? The denominator. Go create another one, you know. If so, that is, we can go from gamma. Okay, we can go from gamma. If you want to, like, because you know you are used to 2 parameters, I can say this, where they have different alpha 1, alpha 2, but they have the same beta. Okay, so this distribution, beta distribution, is used to module proportion. Okay, that's why the range of z will be between 0 and 1. Okay, so the last for today, t distribution. Okay, here we also, you need to know the mean and the variance. Okay, so you can actually, I think alpha 1 over alpha 1 plus alpha 2. Okay, then the variance, we have the variance as well. But because of my time, let me go to t distribution. Yep, we have a t distribution. I think I derived this the other time from the first principle, but you don't need that. I derive it from this guy here. Where z is a random variable that follow us, you know, standard normal distribution, and v follow chi-squared. Okay, we derive. I remember I derive, you know, t distribution. Okay, and of course we use the t distribution, you know, when you are conducting a t-test, where you are trying to compare maybe 2 independent populations. Okay, now the final one was the F distribution. We use F distribution in analysis of variance tests. Okay, F distribution now, the origin of that, if I have a random variable u that follow chi-squared with degree of freedom R1 divided by another random variable that follow chi-squared with the degree of freedom R2. So it's more or less like I have F follow chi-squared with degree of freedom that, V follow chi-squared with the degree of freedom that, and my G of F now is basically going to be R1 plus R2 over 2, F raised to power R1 over 2 minus 1, R1 over 2 raised to power R1 over 2 divided by gamma R1 over 2, gamma R2 over 2. Then I'm basically going to have, you know, R1, R2, F raised to power R1 plus R2 over 2. F distribution, T distribution. Like I said, you don't need to worry about them, but you need to be able to know that we use the F distribution to you know, as you know, a distribution to test you know, when you are trying to test equality of means among independent population. This all, you know, the test that you call ANOVA test, also called F test. You cannot conduct an F test without F distribution. You cannot conduct a t-test without t-distribution. So there are three important statistical distribution, or let me just say four important statistical distribution when you want to conduct a test. Normal. Has anybody heard about z-test? Yeah. Okay, if you don't, z-test is only possible because of normal distribution. Then if you want to conduct a t-test, t-test is possible because of t-distribution. If you want to conduct an f-test, f-test is possible because of f-distribution. If you want to conduct a test where you want to compare two categorical variable that has levels, I gave you an example the other time. Maybe you are trying to look at the relationship between the level of education and your level of income. We use a chi-square test. Okay, the distribution of the null hypothesis is going to be a chi-square distribution. The distributions are more or less like territorial jurisdiction in the court of law. Just like a court want to conduct a trial, that court must have a territorial jurisdiction for the trial. So which means the suspect that they want to try, okay, must have maybe violated the rule of the state. So he has to be tried in that state where he committed the offense. So if I want to conduct a t-test, that would be in the territory of a t-distribution. Because if I use R or use any statistical software, I'm going to take a decision with the p-value. Has anybody heard about p-value? The p-value that they're going to get, of course, we're still going to be doing that in this class. That's what we're going to do next after the midterm too, where we're going to do t-tests, we're going to do different kind of tests. You're going to see us using p-value. And the p-value is only possible if there's a distribution. If there's no distribution for the test, then there's no way we're going to take a decision. If we don't try a suspect in a state where he commits the offense, then if you try that suspect elsewhere, even though another court elsewhere was able to establish the fact that the person committed the offense, whatever decision they take will be declared null and void. Does that make sense? If somebody commits offense in Minnesota, because he needs to be tried in the state of Minnesota because he broke Minnesota law. It did not break California law. Then he shouldn't be tried in California. And if he run from Minnesota to California, then the Minnesota will seek for, we have to contact California to extradite the person to Minnesota. Does that make sense? Because if the court in California does not have a territorial jurisdiction for that. The same thing here. Oh, go ahead. About me. Oh, when I'm done, right? Oh, okay. Now, where am I telling you this? By the time we start what we want to do after midterm, after midterm 2, what we want to be doing is to be conducting tests. But I'm now trying to tell you now, if I say, okay, we want to conduct a t-test, then you should know that we're going to be using t-distribution. If you want to conduct an f-test, you should know we're going to be using f-distribution. If I use t-distribution for f-test, then I'm behaving like someone, a court that was trying a suspect that did not commit the offense in the territorial jurisdiction of that court. And even though they established the fact that he committed the offense, their decision will be declared null and void. Okay, so when you review all of that, what we've done with the assignment solution, you should be fine for the exam. Now, you can ask a question now. Okay, yeah, somebody asked, what is everything you should bring on Monday? When you're coming on Monday, of course, you come with your pen to write, come with your calculator, you can come with two sheets. Does that make sense? I think the same thing as the same requirement with midterm one. Does that make sense now? Okay, make sure you stay safe and have a very good day. But for now, everyone. And you too. How are you doing? Yeah, I'm good. What's going on? Like, other than I think it's content from chapter 8 is not good. No, no, no.